Hello friends, today's discussion is in continuation to the previous one where we were discussing the transistor biasing. The purpose of biasing a circuit is to establish a proper stable DC operating point called the Q point. The Q point of a circuit is defined by specific values for IC and VCE. These values are called the coordinates of the Q point. We discussed that voltage divider bias provides good Q point stability with a single polarity supply voltage and is the most common bias circuit. In today's lecture, we shall talk about other biasing circuits which can be used for proper functioning of an amplifier and their analysis, and finally, learn how to bias the PNP transistor. After completing this section, you should be able to explain emitter bias, base bias, analyze a base biased circuit, explain Q point stability of base bias, define and analyze emitter feedback and collector feedback bias. Voltage divider biased PNP transistor. As you know, a PNP transistor requires bias polarities opposite to the NPN. This can be accomplished with a negative collector supply voltage as in figure A or with a positive emitter supply voltage as in figure B. In a schematic, the PNP is often drawn upside down so that the supply voltage is at the top of the schematic and ground at the bottom as in figure C. The analysis procedure is the same as for an NPN transistor circuit using Thevenin's theorem and Kirchhoff's voltage law as demonstrated in the following steps. For figure A, applying Kirchhoff's voltage law around the base emitter circuit gives this equation where Vth is equal to R2 over R1 plus R2 into Vcc. Rth is equal to R1 into R2 over R1 plus R2. The base current is then Ib is equal to IE over beta DC. The equation for IE then becomes as shown here, where IE is equal to minus Vth plus Vbe over Re plus Rth over beta DC. For the figure in part B, the analysis is like this: minus Vth plus Ib Rth minus Vbe plus Ie into Re minus Vee is equal to 0. Vth is equal to R1 over R1 plus R2 into Vee. Rth is equal to R1 into R2 over R1 plus R2. Therefore, Ib is equal to Ie over beta DC. The equation for Ie thus becomes as shown here, where Ie is equal to Vth plus Vbe minus Vee over Re plus Rth over beta DC. Emitter bias. Emitter bias provides excellent bias stability in spite of changes in beta or temperature. It uses both a positive and a negative supply voltage. To obtain a reasonable estimate of the key DC values in an emitter bias circuit, analysis is quite easy. In an NPN circuit, as shown in figure here, the small base current causes the base voltage to be slightly below ground. The emitter voltage is one diode drop less than this. The combination of this small drop B across RB and VBE forces the emitter to be at approximately -1 volts. Using this approximation, you can obtain the emitter current as IE is equal to minus VEE minus 1 volt over RE, where VEE is entered as negative value in this equation. You can apply the approximation that IC is approximately equal to IE to calculate the collector voltage, where the collector voltage is equal to VCC minus IC into RC. The approximation that VE is approximately equal to -1 volt is useful for troubleshooting because you won't need to perform any detailed calculations. In the case of voltage divider bias, there is a more rigorous calculation for cases where you need a more exact result. The approximation that VE is approximately equal to -1 volt and the neglect of beta DC may not be accurate enough for design work or detailed analysis. In this case, Kirchhoff's voltage law can be applied as follows to develop a more detailed formula for IE. Kirchhoff's voltage law applied around the base emitter circuit in part A of figure here, which has been redrawn in part B for analysis, gives the following equation: VEE plus VRB plus VBE plus VRE is equal to 0. Substituting using Ohm's law, VEE plus IBRB plus VBE plus IERE is equal to 0. Substituting for IB and transposing VEE, we get this result: IE over beta DC into RB plus IERE plus VBE is equal to minus VEE. Factoring out IE and solving for IE, we get this equation. The emitter voltage with respect to ground is equal to VEE plus IERE. The base voltage with respect to ground is equal to VE plus VBE. The collector voltage with respect to ground is equal to VCC minus ICRC. Base bias. This method of biasing is common in switching circuits. Figure here shows a base biased transistor. The analysis of this circuit for the linear region shows that it is directly dependent on beta DC. Starting with Kirchhoff's voltage law around the base circuit, we get VCC minus VRB minus VBE is equal to 0. Substituting IBRB for VRB, you get VCC minus IB into RB minus VBE is equal to 0. Then solving for IB, we get IB is equal to VCC minus VBE over RB. Kirchhoff's voltage law applied around the collector circuit in figure gives the following equation: VCC minus IC into RC minus VCE is equal to 0. Solving for VCE, we get VCE is equal to VCC minus IC into RC. Substituting the expression for IB into the formula, IC is equal to beta DC into VCC minus VBE over RB. Notice in the equation IC is equal to beta DC into VCC minus VBE over RB. that IC is dependent on beta DC. The disadvantage of this is that a variation in beta DC causes IC and as a result VCE to change, thus changing the Q point of the transistor. This makes the base bias circuit extremely beta dependent and unpredictable. And you also know that beta DC varies with temperature and collector current. In addition, there is a large spread of values from one transistor to another of the same type due to manufacturing variations. For these reasons, base bias is rarely used in linear circuits, but is discussed here, so you will be familiar with it. Emitter feedback bias. If an emitter resistor is added to the base bias circuit in figure as shown here, the result is emitter feedback bias. The idea is to help make base bias more predictable with negative feedback, which negates any attempted change in collector current with an opposing change in base voltage. If the collector current tries to increase, the emitter voltage increases, causing an increase in base voltage because base voltage is equal to VE plus VBE. This increase in base voltage reduces the voltage across RB, thus reducing the base current and keeping the collector current from increasing. A similar action occurs if the collector current tries to decrease. While this is better for linear circuits than base bias, it is still dependent on beta DC and is not as predictable as voltage divider bias. To calculate IE, you can write Kirchhoff's voltage law around the base circuit. Minus VCC plus IBRB plus VBE plus IE into RE is equal to 0. Substituting IE over beta DC for IB, you can see that IE is still dependent on beta DC and IE is equal to VCC minus VBE over RE plus RB upon beta DC. Collector feedback bias. As shown in figure here, the base resistor RB is connected to the collector rather than to VCC as it was in the base bias arrangement discussed earlier. The collector voltage provides the bias for the base emitter junction. The negative feedback creates an offsetting effect that tends to keep the Q point stable. If IC tries to increase, it drops more voltage across RC, thereby causing VC to decrease. When VC decreases, there is a decrease in voltage across RB, which decreases IB. The decrease in IB produces less IC, which in turn drops less voltage across RC and thus offsets the decrease in VC. Analysis of a collector feedback bias circuit. By Ohm's law, the base current can be expressed as IB is equal to VC minus VBE over RB. Let us assume that IC is very much greater than IB. Then collector voltage is VC is approximately equal to VCC minus IC into RC. Also, IB is equal to IC upon beta DC. Substituting for VC in equation, IB becomes equal to VC minus VBE over RB. From here we get this equation where IC over beta DC is equal to VCC minus IC into RC minus VBE over RB. The terms can be arranged so that IC into RB upon beta DC plus IC into RC is equal to VCC minus VBE. Then we can solve for IC with this equation where IC is equal to VCC minus VBE over RC plus RB upon beta DC. Since the emitter is ground, VCE is equal to VCC minus IC into RC. Q point stability over temperature. The equation here IC is equal to VCC minus VBE over RC plus RB upon beta DC shows that the collector current is dependent to some extent on beta DC and VBE. This dependency of course can be minimized by making RC much greater than RB upon beta DC and VCC much greater than VBE. An important feature of collector feedback bias is that it essentially eliminates the beta DC and VBE dependency even if the stated conditions are met. As you have learnt, beta DC varies directly with temperature and VBE varies inversely with temperature. As the temperature goes up in a collector feedback circuit, beta DC goes up and VBE goes down. The increase in beta DC acts to increase IC. The decrease in VB acts to increase IB, which in turn also acts to increase IC. As IC tries to increase, the voltage drop across RC also tries to increase. This tends to reduce the collector voltage and therefore, the voltage across RB, thus reducing IB and offsetting the attempted increase in IC and the attempted decrease in VC. The result is that the collector feedback circuit maintains a relatively stable Q point. The reverse action occurs when the temperature decreases. Troubleshooting a voltage divider biased transistor. An example of a transistor with voltage divider bias is as shown in figure. For the specific component values shown, you should get the voltage readings approximately as indicated when the circuit is operating properly. For this type of bias circuit, a particular group of faults will cause the transistor collector to be at VCC when measured with respect to ground. 5 faults are indicated for the circuit in figure here. R1 opens, RE opens, base internally open, emitter internally open or collector internally open. The collector voltage is equal to 10 volts with respect to ground for each of the faults as indicated in the table. Also, for each of the faults, the base voltage and the emitter voltage with respect to ground are given. Fault 1, resistor R1 open. This fault removes the bias voltage from the base, thus connecting the base to ground through R2 and forcing the transistor into cutoff because VB is equal to 0 and IB is equal to 0 amperes. The transistor is non-conducting, so there is no IC and therefore, no voltage drop across RC. This makes the collector voltage equal to 10 volts and also equal to VCC. Since there is no base current or collector current, there is also no emitter current and VE is equal to 0 volts. Fault 2, resistor RE open. This fault prevents base current, emitter current and collector current except for a very small ICBO that can be neglected. Since IC is equal to 0 amperes, there is no voltage drop across RC and therefore, VC is equal to VCC and is equal to 10 volts. The voltage divider produces a voltage at the base with respect to ground given by this equation. When a voltmeter is connected to the emitter, it provides a current path through its high internal impedance, resulting in a forward biased base emitter junction. Therefore, the emitter voltage is V e is equal to V b minus V b e. The amount of the forward voltage drop across the B e junction depends on the current. V b e is equal to 0.7 volts and is assumed for purposes of illustration, but it may be much less. The result is an emitter voltage as given by this equation. Fault 3. Base internally open. An internal transistor fault is more likely to happen than an open resistor. Again, the transistor is non-conducting, so I c is equal to 0 amperes and V c is equal to V c c and is equal to 10 volts. Just as for the case of the open R e, the voltage divider produces 3.2 volts at the external base connection. The voltage at the external emitter connection is 0 volt because there is no emitter current through R e and thus no voltage drop. Fault 4. Again, the transistor is non-conducting, so I c is equal to 0 amperes and V c is equal to V c c and is equal to 10 volts. Just as for the case of the open R e and the internally open base, the voltage divider produces 3.2 volts at the base. The voltage at the external emitter lead is 0 volts because that point is open and connected to ground through R e. Notice that faults 3 and 4 produce identical symptoms. So, friends, here we come to an end of the discussion and therefore, we sum up. Emitter bias generally provides good Q point stability, but requires both positive and negative supply voltages. The base bias circuit arrangement has poor stability because its Q point varies widely with DC. Emitter feedback bias combines base bias with the addition of an emitter resistor. Collector feedback bias provides good stability using negative feedback from collector to base. And finally, we discussed the faults which could occur because of resistance failures. So, friends, that is it for today. See you in the next lecture. Thank you very much.